Recording. Okay, so hello everyone. This is another TFA Technical Forum meeting. The agenda today is Mark Dykes on the TFA team is going to share with us some SMC fuzzing work that he's been doing. And as always, after the presentation and any questions, we'll go through the mailing list if anybody's got any follow-ups that they wish to do. So without any further ado, I will stop sharing and allow Mark to take charge. Okay, over to you, Mark.
Okay, thanks. Let's go ahead and pull up the slides. Can everybody see this?
Yeah, it's full screen.
Okay. Just the morning, afternoon, evening, wherever you may be. Yeah, so my name is Mark Dykes, and I've been involved in this effort to try to introduce the concepts of fuzzing into TFA. This is sort of the first foray into this arena. And so just a little bit of background from myself. I've been involved in CPU verification for quite a number of years. And my principal goal at that time was to have fuzzing techniques to really do CPU verification in a very exhaustive way. And so when I transitioned over to TFA, I noticed that there was some potentials that could be utilized in that same place where we could have fuzzing in that type of paradigm where we could potentially leverage things that we had some advantages in the CPU verification side. So to that end, I just wanted to kind of introduce the concept, get an overview of what it looks like, and how it's currently being proposed to be implemented. And right now, it's actually implemented in the way that it's in the fashion that it's shown here. There's quite a few tweaks that we still have to implement, but it's still a work in progress. But it's largely how it's represented here, how it's actually being implemented today. So first thing I'd like to do is just sort of have a justification for the directed randomized kind of approach. So we have essentially behavior tests that will be utilized using seeds of various kinds. So the first thing I would say is, you can exercise many more code paths with this type of testing. What you would like to do is, as opposed to say directed tests, is try to exercise as many code paths as possible without having to write directed tests for each of those things, and possibly also think of them as well. It's very hard to come up with a strategy using a directed test approach where you're saying to yourself, okay, if I want to have as much as possible going on, say in any given test, I have to write code to support each of those code paths. And it's very difficult to do that, at least in directed approach. And it's much less efficient, I would also say. Due to that, we have a better ability to find bugs and coverage points with what I would argue is much less effort than directed tests. And I think that's pretty much borne out in the actual industry. So we would like to have the randomized try to hit those paths that otherwise, as I said, could not be thought of initially. And so it's really useful to have gaps between their different randomized points in the test to be able to cover those paths that you otherwise would not have thought of. So additionally, we have increase in effectiveness with time versus issues can be found when time is increased or more operations. It's certainly something you can't argue with for directed testing. You would, with that type of thing, for directed tests, you would just simply say, well, okay, I would have this set of directed tests in order to cover more things in the future. I would have to write yet more directed tests. That's not the case with the randomized approach. So what you can do is simply apply more seeds and come up with more testing strategies and different things that could happen just by having more time. So it's a much better, I think, in the long run approach to try to ferret out bugs and different types of issues. So the next point was sort of plays into that and dovetails actually better at finding issues with large state space variables. I think that's pretty much as a given, as I think I've justified before. And events and functions can be reordered in many different ways. So this is, I think, a critical area that I think has to, which bears further explanation, particularly if you have multiple CPU nodes. What we would like to do is have the ability to run functions that could parallel other functions going on with other CPUs. So you could say I have one type of SMC call occurring on one type of CPU, and then the second or third and fourth CPU could be running another type of SMC call, and all of those are randomly called, and the timing amongst that occurs in the differentiation between these different CPU nodes is also utterly random, which is very useful, I think, in trying to emulate as much as possible a real world scenario, rather than trying to do a directed approach across all these different CPU nodes using a sort of a very fixed type of parallelism. And you can potentially reduce test set, since each of the tests can be leveraged in many different ways. So all you would have to do is simply have a set of seeds that will be applied to a given test over a period of time, and it would still be of maximum use to you to find other issues that you potentially could not ever think of otherwise. So I would also say that you would have the ability to think of the test as being more rules-based rather than trying to just control the code itself. So you would say, okay, I want event A randomized with event B. I want them randomized with regards to how each of those events occur either before or after each other, or maybe perhaps at the same time, if you're talking about different CPU nodes. So you would think of more in the paradigm of believing that you could organize things in a way that's much more conducive to how we think, rather than trying to do and artificially create something in the nodes themselves that I think would work against you in the long run to find issues. Okay, so this is a basic overview of what in particular, we're trying to approach SMC calls within TFA. So you would start with, say, a given test, say within EL2, and at the top level, it looks simply just like this. You'd have a random SMC. What that does is it falls into what's called a general SMC constraint type of engine selection, which then offers the ability to crank through that to create an actual SMC call variation. Once that's done, then you would then have the ability to know, okay, once I have a particular flavor of SMC call, what type of arguments do I want to apply that in a random way? And then once again, you would go back to the constraint object itself that would contain all the different constraints you would want for that particular environment and for that particular test. And then you would constrain those variables based upon what you may be looking for, or that type of scenario you're looking for that particular SMC. Once you have that specialized SMC call, you have the random argument inputs, then out the other side, you get the SMC call itself, which is then put through the system. And then you would do this on a per CPU basis as required, and to introduce as much parallelism as possible to see that. So just an idea about the constraint properties themselves. So you could, as I implied, you could have a user to tailor the testing to a particular area of interest. So I think if you're interested, say, like in power scenarios, or you're looking for more intensive types of memory operations, you can bias the actual testing itself to try to direct it in that direction without completely overtaking the entire paradigm of what you're looking for the testing itself. So you could still have other things happening in the background, quote unquote, but then your primary testing may occur on that particular type of scenario, particular functionality you may be trying to exercise as much as possible. So let's say, for instance, if you have a bug that exists in one of the modules that you discovered recently, and you know, okay, if I have this particular bug that occurred based on these conditions, what I can do is sort of fuzz around that and still try to do as much of those scenarios that deal with that functionality as possible, while still maintaining some of the other randomized approaches that you may have occurring in tandem with it. So it's really useful engine to try to have that type of an arrangement to try to work around the bug and see if other bugs might exist within that same space. So to that end, we have multiple layers of biasing among the options. And of course, there are certain instances where you may say, okay, if I have a particular condition that occurs based upon test scenarios that I'm interested in seeing, you can override that randomized behavior and say, okay, I want to constrain it to this particular thing without having to do a lot of jumping through hoops to get that to work. You would simply go to one file and say, okay, I'm interested only in seeing a very constrained approach for this particular scenario, only limited to, say, this type of SMC call with these types of arguments, but maybe and fuzz a little bit around that. So you can take the whole cone of randomization and push it down into a space that's much more reasonable for any given scenario that you may be looking for. So because of that, you can actually reduce what the next statement says. You can have a directed type that can ultimately result from the randomization engine itself. So you can, the whole idea is to have a type of approach where when you're doing randomized or regression testing, you have as much randomization as possible. And then as you push down and find issues, then you can gradually constrain it in a more narrow way to maybe see other things that you might not have seen otherwise. So it allows change of constraints for invocation of the random SMC. So that's something that's still a work in progress for us, particularly for the seeding strategy that has yet to be fleshed out. We have object type to be manipulated as any data object would. So the thing I probably didn't emphasize enough is the constraint object itself is essentially a global type of thing, or where you can use it as a variable inside the actual testing structure. So you could have multiple constraint objects that would have the ability to constrain a particular object. I'm getting some noise here. You can have the ability to have a constraint object that would have multiple types of constraints within, not only for SMC, but for the variant of SMC call, you could have multiple arguments that they could be constrained in a very specific way, depending on what you're looking for. So the constraint object would have that. Then once you have that type of arrangement, then you could have multiple constraint objects that could be potentially contained in a library to be utilized for future testing if that's what was required. So if you noticed, for instance, that a particular bug was manifested whenever you had a particular constraint object with that particular seed, you would run that and say, okay, I've seen a bug here, and once I know that exists and I fix it, then I can take that very same seed and that very same constraint object and put into a repository of some kind and say, okay, I can always reference that later and make sure that bug never shows up again based upon future types of iterations of that particular of CPU and or system. So what this is here, this is what I call a bias tree model of SMC selection. So this is a representation for how the SMC call actually will manifest itself based upon how a user might constrain the object going forward. So the first thing you would do is you would have, say, a bias list of general SMC calls. So here, what I've done is they're just given a generic type of labeling to the different variations of SMC calls themselves. But you can think of this as being more like, okay, I'm going to do an SMC call based on SDI, or I could do an SMC call based upon some power scenario, or GIC types of testing, or what have you. You have the general types of representations on the far left-hand side. Each of those is assigned an actual bias. And then what the engine does, the way that it works now, is it goes through the process of looking at each of those different variations, and then chooses amongst those SMC calls based upon the bias that you see here. So, and it doesn't have to be, of course, 100 point based. It could be any type of bias arrangement you would like. And once that's done, it goes through the process of making that selection, and it moves on to the next one. And then it falls to, okay, if I have this particular SMC call at the top level, and I go to the second level, then get more SMC call variations that could exist below that. Each of those, once again, has a bias that's associated with it that it chooses amongst, and it keeps doing this iteratively until it finally ultimately results in an actual SMC call that can be utilized by the system. And this would be just the general way that every SMC call would be called, and you can see how all the different biases will result in sort of like a tree, and you can specify that at the top level. And what I'll do later is I can show you how the actual file looks, because it's based upon more of it's a device tree file that you can use to set these biases and do it in a way that it's hierarchical rather than a straight line type of arrangement. The thing is, I think this is much more conducive to doing a real life type of scenario where you have different types of testing that can occur, and you can emphasize something, say at the top level, say I want to do more of this type of testing, put that bias higher, and that way they'll result in much more frequent testing of that particular type of scenario you may be interested in seeing. And then you can subsequently go into all the other variations that are contained below that and set the biases accordingly, depending on what type of thing you may be wanting to see. So in this way, you can narrow the cone of randomness, where you can have different types of SMC calls that are constrained in a very specific way, and then push it down to a very, very low level and get more of a directed test approach if that's what's desired. But then you can always at any point step back and then say, okay, I want to open the spigot, if you will, and let the whole of the randomization occur as you would like. Is this somewhat clear? Do you guys have any questions on this so far?
Well, I have one question, right? So this is more useful for catching issues like crashes or panics and stuff like that, right? I assume this does not have like expected results or anything like that, right?
No. Okay. So what I do is I'll address it further in the slide set, but you'll see exactly what I mean when we're doing the checking itself. It's not just panicking or hanging. there's other potentialities that you could have for checking different types of things that you may be interested in seeing. So yeah, there's more utility to it than just that. Does that make sense?
Yeah, thanks.
Okay. Any other questions for anybody? Okay.
Hey, Mark. So just wanted to understand, is this bias tree, like it starts with some basic, and then as the fuzzing tool keeps running more tests, it builds on the bias trees? Is this something of that sort, or is the bias tree static at the start time, and the SMCs would always be built from whatever has been decided at the start?
Okay, that's a good question. So the actual bias tree itself is static. So once you declare it, then it remains as is throughout the entire duration of the test. So what you would like to do is, if you're interested in seeing different types of how the bias tree might manifest itself with different types of testing, you would just have different constraint objects that would have bias trees with different biases contained within. But yes, it is a static entity.
Okay. Yeah, I mean, the reason for asking this was in my past experience with fuzzing, I've worked with models which start at some basic, and depending on how the target behaves, they keep on updating their side of things, and they try to evolve so that they can catch more issues. And so maybe this is something different. Maybe we'll find out once we move on with more slides.
Yes, so it's interesting you bring that up, because there was some experience that I've had with the fuzzing, in particular CPU verification, where we would do that. You would apply based upon the behavior of the model or the system that you're trying to test, and you could change the actual bias tree structure itself and do different things. That's something we could certainly entertain, but I think coming out of the gate for now, it's going to be a static entity, and then over time we can probably evolve into something more sophisticated like that. That's certainly something we can entertain, I think. Does that make sense?
Right. Yes. Yeah. Sounds good. Thanks.
So the random SMC call will accept a single constraint, as I was saying. It will contain all the biases needed. Right now, that is not fully fleshed out, but it's something that certainly will happen probably in the near future. So the constraint object will have access methods to modify any of the biases across all hierarchies. So let's say that if you're looking at doing a type of testing that not all the constraint objects that you have as library access to would exercise a particular feature that you're interested in. And you can just take the constraint object itself and say, okay, I'm just going to modify a few biases within. You have, like, I don't know, some lines of 10 lines of code to make the constraint changes for the biases, and then you resubmit, and then you're good to go. So we tried to objectify as much of the constraint object itself such that it's transferable and or modifiable as much as possible by the user without having to go through a lot of hoops to make those biases to change. So this line here with the default biases will be set to 50. That might be deprecated. I'm not sure. We may change that. Oops. Okay, so the functions can be provided that will set the biases and the constraint object for interesting combinations or even random biases. So my thought is, and it's something I think for someone that may be a platform owner or something we may have a feature in the very near future, you could have your own set of constraint objects that you could apply to your given types of platforms that will exercise your particular functionalities you're interested in seeing. And maybe in the future, we could provide a basic set of constraint objects for the fuzzing that would exercise things that we would consider important for the basic functionality we're looking at for ARM. And then others could use other types of constraint objects to build their own libraries of constraint objects to see more interesting things that they're interested in seeing. So SDL and security hardening, other types of biases could be employed to cover special SMC calls. So let me just address this point, I think, quickly, because I think it bears a little more explanation. I think when you're talking about SMC calls that are where you're transferring, say, from the normal world to the secure world, that's a sort of a hot point for security. So I think it would be of interest to know how we could apply SMC calls for different types of security scenarios that could expose things that we may not have otherwise thought of. So let's say that you have a set of SMC calls in your particular platform or your particular implementation that do very specific things, but if you were to say, go in and say, okay, I want to have a series of SMC calls that do essentially nonsense. Okay, if I go in like a hacker would do and just start pounding it with different SMC calls that could, if you will, mess the system up in some way or expose a vulnerability, I think the fuzzing is an ideal engine to employ for that type of testing. I think what you want to do is say, okay, if I have a security vulnerability for a particular SMC call that could expose some type of a problem, then you, as I said, similar to what you would do with a bug, you would start applying other SMC calls that could be fuzzing around that, but not doing coherent calls, if that makes sense. You may be doing other things that are outside that, the idea of having a directed SMC call do a very specific thing, but then you want to sort of randomize on top of that to say, okay, are there other security vulnerabilities we may have missed before? So you would have a separate library of these things that you could then apply for constraint objects just for that purpose, and have security be a consideration when you're trying to find holes that could be potentially opened by SMC calls, and with different SMC calls that could expose memory issues or what have you going forward. So what I'd like to do is just sort of address the whole checking idea. So this is the basic format of what it would look like at the lowest level. So you would have the bias tree then set up, you would have all the biases contained within, you would go through the SMC, the bias engine would go in and select a particular SMC call. At that point, this is when this diagram takes over. So you would see an SMC pre-call. What that would do is to say, okay, if I have this particular variation of an SMC call that I know, I have this set of arguments that will apply to it, and then I would then apply a set of rules to say, okay, if it's a particular type, based upon some other randomization that I may be interested in seeing, it will then fuzz the arguments going in, and then the SMC call will occur. Once it returns, then we do an SMC post randomization phase. We check return status, and then check potentially the system itself to see, okay, how did it affect things? Did this particular event occur? Did it not occur? Was there an interrupt? Other types of things I think could be put in that space to do the checking itself to know, okay, did it do what I expected it to do? And this could be as simple as just ignoring it, or it could be something very sophisticated that would go in and then do a system interrogation to make sure the SMC call did what we expected, or maybe not what we expected, and then flag an error if that's the case. So hopefully you would have some reasonable way to do the checking once the SMC call returns. And this is essentially the same approach you would have with a directed test anyway. A directed test would then do the same thing where it would say, okay, I'm doing a particular variation of SMC call. Once that returns, I check the return status logically. Of course, that makes sense. But then you may want to do additional checks on top of that would fit in the space that we see here. So a few considerations. I think it's important to know or take note of the fact that all SMC invocations should exist as autonomously as possible. We don't want a lot of dependency, say, between the SMC calls, if possible. I mean, because if you have that dependency, then you sort of have to start constraining the SMC calls one from another, and that tends to gum up the works for the randomized approach. But I'm not completely ruling that out. I think at some point it may make sense to start having a fuzzing from a higher level than just SMC calls themselves, and maybe a series of SMC calls we may want to do in a fuzzing that we could also start considering as a possibility for the engine itself. And I certainly think that's well, it might be a good thing to come in order very soon. So to that end, the state of the system must remain the same between the calls as much as possible. We don't want the system to change too much, because if we have a series of SMC calls coming through, it's much easier to have the system stay as the same, you know, with regards to memory or some other things. Certainly things will change, but you don't want to see like a change of EL or something like that may cause some major issues that for checking particularly, and other things that could make the whole system come off its rails. So you must have a common error/warning handling protocol in place. This is something we have to yet to address in any significant way. I think right now most of the error checking will occur in the layer that I referenced earlier, but we need to have a better commonality amongst all the different errors that we see now. I think that's something that could still be a work in progress to have resolved. And also this can work in parallel with the directed test without issues. So you could have, say in your regression suite, all your directed tests as they exist today. And then with that, you would work with the randomized approach and biases. You can introduce as much randomization as you want or as little, and then you can gradually increase that over time as the constraint object library grows. And if you find a bug, then you can start fuzzing around that, again, adding to the library and becoming a little better at finding these types of issues. And then we'll address the methodology to address vendor-specific types of testing coming up in the future. So right now, this is an example of an SMC bias tree using the device tree format. So what I've done is I offer here a breakdown of what the device tree file would look like on the left-hand side, and then sort of a representation for what the biases would look like amongst all the different variations of SMC calls that you see on the right. So it's fairly straightforward. So for every node that you have going in as far as the top of the hierarchy, so you see the SMC 32 fast, SMC 64 underscore fast, that's the general category. Below each of those, you have a bias associated with that. And then you keep going down until you have what's called tree nodes. You do the SVC UID, and ultimately that's the actual SVC, or I'm sorry, the SMC call. And there's a bias associated with each of those variations, and then an actual function name that will be applied in the system itself. So the function name for that SMC variant will be actually invoked, and then it moves on to the next SMC variation and then traverses the tree yet again to find out what that other SMC call would look like. It's kind of a complex diagram. Does this make sense? Any questions on this?
Yeah. Oh, sorry. So I had a question, right? So what about the arguments to the SMC, right? So it looks like you pass the device tree, and then based on the bias, it sounds like what probability you would use to call, let's say, SMC affinity or whatever, right? So do you randomize the inputs to it, or are the inputs to each SMC fixed?
It's whatever you want to do, but you can randomize the inputs, and that's something I would suggest that you do. So, and if I go back in the slide set, so what you see is that SMC pre. So all the setup occurs here. So we could randomize the inputs into the SMC call using that layer. And then once we know that that particular SMC call will be invoked with randomized arguments, and then the SMC post would then be responsible for checking and making sure that it occurred the way we expected. So the randomization would occur at that layer. Although we don't have the same type of setup for the actual arguments going into the SMC call in a bias tree. So that's a responsibility of the user, at least at present, to randomize that particular set of variables. And so all of that is on the table. You can do that or not, depending on how you want your system to look. Right now, what this is offering is the SMC is just a way to have the SMC call itself be randomized. And then later on, we'll address more specifically how we could do the same type of model, perhaps, for the arguments themselves. But it's easy to randomize the arguments for most SMC calls, since there are not that many. They're going in.
Okay. Okay. So the function name in this slide effectively encapsulates the pre-SMC and the post steps. Is that a good way of thinking about it?
Yeah. That's one way to put it. Yes.
Okay. Thanks.
Yep. Okay. So the current status. So the prototype is basically done. I'm pushing the actual changes today, to be honest. So everything is there the way that I have stipulated in this presentation. There's the thing that's probably remaining is we have yet to address the seeding in a coherent way, and then the constraint object itself is still a work in progress. Other than that, everything is working as it's shown here. So it'll be integrated into the FIB. So kind of some of this information is actually dated. So there's no memory limits issues as far as I know. So the focus will be initially to randomize the flavor SMC rather than the inherent arguments, as I said. And we'll begin with one CPU, but we'll begin also with parallelism probably within the next 6 months or so. So we'll have parallelism introduced as well. So yeah, so that's dated. Don't ignore the rest of it. All right, so the usage model. So right now, the way that it's actually architected is in the actual TFTF, you'll have a separate TFTF config file that will specify that we have an argument for the device tree itself, where you'll see the random SMC, and then over time, the second one will be supported, where we'll have a number of tests that can be invoked potentially for that variation going into the actual testing itself. So what this is saying is, if I have a particular device tree file that I want to see, and that would represent the device tree that I showed you in the previous slide, I want that exercised here. That will go into this particular FVP TFTF config, and then we know that variation will be exercised. And then on top of that, there will be some number of tests that will be invoked based on what the user requirements. So that could be anywhere between 1 to 100 or however many you're looking to see, depending on how much time you have on your particular regression engine. So this is just an example right now, and it will probably be realized in a short order. This is data and information. So all of this is now resolved, so it's not a big deal. And that's pretty much it. Do you have any questions?
Hey, Mark, Varun here. So yeah, I have a couple of questions. The first one, I'm just curious. There are so many other engines out there, so just wanted to understand if you used any of them as the base for building this, or do you start from scratch, and the thought process behind using your own if you did not choose a readily available one. I know there might not be something that fits our needs directly, but there might be something that is of value in other engines that can be also leveraged.
Yeah, so there was some thought given to other engines that I considered. I think it was the American something. There was another fuzzing engine that I had considered and actually looked at before. I think the big consideration for us was memory limitations and FIP limitations and different things that if we start importing libraries from these more sophisticated types of fuzzing engines, it may present problems for us and the constraints that we have, in particular for TFA. If it was just a general type of programming type of paradigm, I think it would have been simple to use those other types of fuzzing engines. But because we're constrained by memory and so forth, it's a little more problematic to try to incorporate those here. However, going forward, it's something we might think about as well. If that makes better sense, we could look at that. I think your reference is fairly clear, because I think what you're saying is we could iterate the bias tree over time, depending on the system state, right? Is that what you mean? That we could have that for free essentially if we would adopt those tools. Is that clear, or we were driving to?
Yeah. I mean, yeah, that was one of the points. But the American fuzzy loop is the one that you reference. Yeah, they have a lot of intelligence built in over the years. So I mean that was just an example. I'm not saying that we need to change something here. I wanted to understand the thought process, and yeah, if it makes sense, then yeah, it can be revisited. Another thing that I wanted to understand is there any dependency for platforms, for example, on device trees or any of the other configuration that some of the ARM platforms might use, but the other platforms might not have started to use? I know the Tegra platforms don't use device trees, and I think in your slides you talked a little bit about device trees, so I wanted to understand that part.
Well, okay, so the device tree itself is nothing more than an input to the fuzzing engine. So it's not, the platform would never see it, right? So this is more about how the actual TFA would absorb the information, and so the platform itself would not be required to know it, right? If that makes sense. So it's inherent to TFTF, and it will never be seen outside of that context.
Okay, so okay, yeah, okay, got it. And I just wanted to understand the approach that the fuzzer takes in case of hangs or resets or reboots. So if something like that happens, does it restart from scratch, or does it take that into consideration and builds on top of it?
So that topic has yet to be addressed, I think, in any significant way at this point. If it hangs or does something, I think it's more implementation specific of how that might be handled. So it's really beyond the context, I think, of the engine itself, how the system responds. So if you have something like that, you have to have some type of timeout mechanism or some way that you, even with a directed test, would have to have the same type of handling of those types of things, if that makes sense. So if I'm writing a directed test and I see a hang, directed test has to have a timeout there that's inherent for that particular scenario to ferret that out and inform the users that's what's happening. And I think the same thing has to occur here for the fuzzing. So whatever directed test approach would have to be also emulated for the fuzzing. Seeing that. Is that clear?
Yeah. Sorry, one more, maybe the last one. So in case of all these, if you find something and you want the engineer working on that issue to reproduce the same exact failure again, so I assume there is a way to do that without having to run the entire fuzzer again, right? I mean something like a seed value.
Yes, exactly.
Use that
That's exactly the point. So as long as you have the same constraint object and the same seed, it's no issue to reproduce that. So once you know a particular scenario has run, you know that what the seed is, and the constraint object, it's easy just to say or apply that same seed and get to the bug. So yeah, that will be there definitely. It's something I've learned in my CPU verification days.
Right. Okay. Yeah. Thanks. I'm going to shut up now. Thank you.
No problem. Anybody else have any questions?
Yeah, quick question. So the engine is sort of abstract, right? It is not. It's not tied. I know you're using it for SMC fuzzing, but it's not tied to SMC fuzzing in any way, right? So in theory, I could use it to test memory management of TFTF itself if I wanted to, for example, right?
Yeah, no problem. I mean, it's not required that you use SMC fuzzing specifically for this type of engine. I mean, it's a bias tree that could be used for anything. Okay. So yes. So, but the thing is, we'll build it as an SMC fuzzer for our application, but yes, it could be used for other things as well. And so there's nothing to prevent you from that. And we could talk about sharing those types of scenarios if that's something that has some interest.
Thanks.
Yeah. Any other questions? Okay. All right, Joanne, I think we're good.
Okay, thanks, Mark. Let me reshare my screen. Share. Hopefully you're seeing the agenda slide. So thanks, Mark, and interesting session on SMC fuzzing. I've got some questions, I guess, for everybody really. We've had sort of about 6 or 7 of these tech forums now, and they're bi-weekly, and every time generally the subjects in the agenda is sort of decided by, well, effectively me and the team, the ARM team. But it is open for anybody from any of the partners. If you want to present something, yeah, I would like to promote that. We've got some other subjects that we're looking at in the future that we could present, and of course we're trying to use these sessions for new work. It's not only just sort of stock slides that we have in different areas that we can present. It's also as we're working on new features and things that we want to share from a sort of a design review perspective, that's what we're trying to use these sessions for as well. But I would like to sort of promote, all our various contributors to do similar. If they want to present something or thrash out a design review discussion about a certain area or feature that they're interested in and they want to present. So I would encourage you guys to do that, and do approach me and let me know either directly or on the mailing list, and we can organize these other sessions. And I'm also open to subjects if folks have got things they're interested in, because basically you're going to get it as and when I decide or the team decides there's something that we're going to do each week. But if you guys have got some subjects that you're really, really desperate to talk about, and you want to hear from us, the sort of the ARM side of the project, do please again let me know. You can let me know either now or again direct email or on the mailing list. So, is there anything anybody wants to say, or any subjects folks want to hear from in the near future?
Yeah, I'm really interested in SPCI and the plans for hafnium and yeah, what the plans are there and what's going on there. That will be useful to talk about and discuss. That's a topic I'm very interested in, and TPM as well.
Sorry, what was the last one?
TPM.
TPM. Okay. Yeah, so definitely the hafnium SPCI, that is one of the ones I've got on my list, and I've asked Olivia to on the team at ARM to prepare some material, but we can talk about some of the others. I mean, if you've got some questions that for hafnium and SPCI, that there is obvious things that we can present. For TPM, if there's something you particularly want to know, let me know. Or if you want to present something, that's another option. All right. Okay. Anything else from anybody? All right. Okay. Not heard any more. So I guess we're at the point now. Well, we've got about a quarter of an hour that. We have this sort of stock section about discussions for things on the mailing list. So this is our opportunity to follow up any of these threaded discussions that we've had on the mailing list. Generally in the last sort of 2 or 3 weeks, really, since the last session. So so this is hopefully you guys can see the screen. Do shout if you can't. This is what we've been discussing effectively this week, I guess, for that we've had on the mailing list. Hopefully the issues with the Gerrit server is resolved now. I do know that's happened a couple of times over the last 2 or 3 weeks that we've had to get the servers fixed. If there's nothing in the June that anybody wants to shout about and they want to talk about, we can go back to May and look at any of these items here. Is there anything anybody wants to follow up on? Okay, I'm not hearing anything, so I guess there's nothing particular on anybody's mind that they want to talk about. I guess we can have a general chat if there's any other issues folks want to raise. All right. Hello.
Hi there. Yeah. I'm Akash. I would be interested in hearing. So going back to the previous thing where we were asking about topics. So I'd be interested in hearing if somebody did a migration of TFA from an older version to a new version. So if they can kind of go through what was their approach and what were the problems they encountered. I think that will be interesting.
So you mean one of the consumers for one of the partner platforms who've gone from an earlier release, sort of TFA, to one of the newer releases and issues that they've encountered? Is that what you're talking about?
Yeah. For example, in the mailing list, you can see like somebody is working on migration from 1.5 to 2.3, which I think is a significant jump. So
yeah, actually I have done that myself, Pankaj Gupta. So I was doing it for NXP platforms from TFA 1.5 to 2.3. Yeah, so
I mean, I think
sorry. Yeah,
I was just going to say, I think it seems like an interesting challenge that you've taken up, and it'd be interesting to know what problems you came across and what was your strategy.
yeah, so I started I started with so you want me to present, or you want we can discuss now? for 10-5 minutes.
Either way, I mean, if you can spare time to present, I would be very interested. I don't know if other people would be, but
Yeah.
that's definitely something that I'd be interested in. But if you want to mention something about it now, that would be good.
Yeah. So briefly, I can talk about now because yeah. So briefly, I've just cloned the 2.3 repo, and see, we are working on earlier with 1.5, and so we are supporting currently around 10 to 12 platforms internally on our internal repo on 1.5. But yes, we decided to move to 2.3 and upstream that, and so we picked up one platform out of that, and so we cloned the 2.3 and ported our whole work, which is part of the Plat NXP, to 2.3. And so the challenges which I faced is so we have when we are modifying the whatever the dependency we have for the common code on of TFA. So we have separate commits as part of 1.5. So we have a separate listing. What is dependency we have on common code of TFA, and so we analyze that first. What are the changes corresponding to 1.5? Like we have macro definition changes for trusted board boot, TBBR feature, and there are different approaches being followed, like placing the like general guidelines for the coding that is being but majorly from the functionality point of view, the things are already identified. So the major dependency is the common code which we are impacting of TFA to accommodate our platforms. Rest of the things are as is being taken care. So there is not much effort putting taking to 2.3. But yes, making it upstream, so that is a separate issues which reviews and all that is something separate. But yeah, porting from 1.5 to 2.3, whatever is a common code is the only issue. Otherwise, rest things are easy to do.
I see. Did you try to break it up into different stages? Did you kind of do like certain bits first and then?
Yeah. So yeah, I've broken down so first to start with console logs to be the first, whether I'm able to get my console prints. Then moving ahead with the DDR initialization. So incrementally I moved on and see that the stages to reach, like then the BL2 is successfully able to load my BL3231 BL and I'm able to reach to U-boot prompt. So this is as part of non-secure boot, like non-secure or non-TBBR flow, normal flow. Once that's normal flow is achieved, then I move to the trusted board boot flow, whether that trusted board boot flow is working, and then add on features which are NXP specific features which are relevant to TFA. So that is the incremental approach I took. But yes, the console is the first thing, so that I can that will help me put the debugging logs and all.
Right, makes sense.
Yeah.
Thanks.
So could have when we do the releases, could we have done anything better to support the migration? Is there anything we're missing out? Because as you know, it's basically every 6 months we effectively tag the end of the tip of the tree, go through our test, some internal tests and things that we have, and then you get a tagged release. But is there anything better that we could do?
Well, not so I did this once from 1.4 to 2.2, and I mean I guess this is more of a problem for non-upstream platforms. So I guess it's not highly motivating to make things easy there. But yeah, one thing is there's a whole bunch of weak functions in the TFA code, and you know when you what we did was we just cloned a fresh repository of 2.2. Wiped out our platform port, you know, compiled just the 2.2 code first, and then pretty much created a platform port from scratch, right? And there were some interfaces that were changed. There were some weak functions, and because of the restructuring of make files, yeah, even though the platform compiled, what we found was, oops, there are some default functions that are, you know, being used automatically because of the way it's been restructured, right? So yeah, it would be one thing that would definitely make things easier, at least from my point of view, is to start getting rid of weak functions. I know it has its place, but yeah, I think that would be something of interest from my point of view.
All right, okay, that's interesting. And any other things that you feel, you know, releases should provide as information or anything when we do the tagging?
I think it works well for upstream platforms, so I don't think there's any, at least I don't have any complaints there. Yeah.
All right. So we got 4 minutes left. Any other questions, areas that folks would like to talk about in the last few minutes? I'm not hearing anything, so I guess we can finish this meeting, and thank you for everybody for joining. Again, there'll be another one in 2 weeks, and we'll see if we can if we ready to do something about Hafnium if possible. But if not, we'll find hopefully something interesting to present to folks. Or if you guys outside of ARM want to present anything, as I said, do reach out to me. But apart from that, thank you very much, and speak to you on the mailing list, and again in a couple of weeks.
Thank you.
Thank you.
Thank you. Bye-bye.
Thank you. Bye-bye.